All right. Welcome to the second class, folks. We're going to have a little redo of our name tags because the little name tags you wrote in the last class were written with your pens, and they are not visible to me. So we're going to hand out more paper, and we will give you marker pens so that you can write your names out in nice bold characters and I can read them. As usual, please shut your laptops, phones off, everyone. Laptop shut, please. You guys at the back, laptop shut, please. All of you. Can you shut your laptop? Okay. The attendance is on poll number 69, if I'm correct. And let's begin. So we just went through the introductory lecture. In the last lecture, I kind of apologize for how the lecture was held. I'm not used to speaking at the podium into a microphone. Fortunately, today we do have our lapel mic and my remote clicker, so we should be better. Today we're going to cover, we introduced what a neural network was, the basis, the cognitive basis for the original models for neural nets. And what we have these days are far more complex, but the principles that we began with still hold. So we're going to continue with that introductory lecture, except today we're going to go a little bit deeper into what these artificial neural networks can represent and what their limitations are. We keep hearing of things like activations, depth, width, and whatnot. What are these terms? And how do they influence what the network can model? So for a quick recap, we found in the last class that a whole lot of tasks that were assumed to be essentially a function of human intelligence suddenly became possible not many years ago, but through the use of neural networks. And now they've taken over the world. And we found that these neural networks are basically these boxes that take in inputs and compute outputs. Now, what are boxes that take in inputs and compute outputs? They are functions. So the question was, what are these functions? And we found that these functions are, in the human organism, these functions are computed by the human brain. And so artificial neural networks kind of mimic the structure of the human brain. And we know that the human brain is composed of a network of very simple computational units, where each computational unit is just the neuron that's shown to the left over here. And so we begin with a model of the neuron itself. And the actual artificial neural network is a network of these neurons. Now, in the simplest structure, the neuron is, do we have pens here? Yeah, pens, chalks. So the neuron is the structure which takes in a whole bunch of real valued inputs. It could be real valued, it could be Boolean. It computes a weighted sum of all of these inputs and compares this weighted sum to a threshold. If the weighted sum exceeds a threshold, the neuron fires, otherwise it does not. And so here is the structure of the neuron. You have a whole bunch of inputs. Every one of these inputs has a corresponding weight. So you get a weighted sum of inputs. You compare this to a threshold, and if it's greater than the threshold, it fires. So this neuron was what we called a perceptron. Electrical engineers are also going to be familiar with this term. If the output is Boolean, it's called a threshold gate. Every one of you who's an electrical engineer must recognize this little structure. So we can actually redraw the structure. And so we're going to do this. The way we did it initially, we just said you had a bunch of inputs, and all of these summed up. So we had summation wi xi, and then we compared it to a threshold. Is this sum greater than a threshold or not? If it was greater than the threshold, the output was 1, otherwise the output was a 0. I can rewrite it like so. Instead of saying is summation wi xi, where xi's are the inputs and the wi's are the corresponding weights. Instead of asking is this greater than a threshold, and the answer is 1 for yes and 0 for no, right? The greater than or equal to, just to make sure that all cases are covered. I can redo this as by saying is summation I wi xi minus t greater than or equal to 0. These two are the same question, correct? So, but once I begin drawing things in this manner, I can redo my model like so. I can just say I have my xi's, and corresponding to each one, I have a weight, Wn, W1. I'm going to sum them all up, but then in addition, I'm going to sum up a bias term, which in my case is simply minus t. And so this gives me a value, which I'm going to call z. And this goes through a function, which is a threshold activation, where the output is 1 if the input is positive, and the output is 0 if the input is not. And these two models are exactly the same model. So what we are doing over here is to first compute an affine function of the inputs. Again, what is an affine function? Does anybody remember? Yes?
It has an offset.
It has an offset. So if I have something like this, summation wi xi plus b, this is affine. Summation wi xi is linear. Where does this term come in? If I equate this to 0, this is going to represent the equation of a line or a hyperplane that goes through origin, whereas this one represents the equation of a hyperplane that can intersect the axes at any point. So that's the only difference. And so now what we're really doing here in this model is to compute an affine value z, and then you're passing the affine value through an activation function. Get used to the symbol z and to note the term affine variable, because we're going to use it again and again in class. And so once I do that, I can actually replace this threshold activation here with other activations like a sigmoid, or which is a soft version of a threshold activation, or other things like a tan H, or things like the soft plus or the rectified linear unit that you will get used to pretty soon in class. So for the purpose of this lecture, we're going to continue assuming a threshold activation, because threshold activations are the ones that are the most intuitive to understand in many senses of the word. There's a poll. Can everybody hear me? Yeah. So this is an easy poll. We have 20 seconds to go. All right, so these guys are done. Mahima, is the first one a linear combination? Yes. Does everybody agree that the first term is a linear combination? Right. Miguel, what about the second one?
It's an affine.
It's an affine. Why?
Well, it's a hyperplane because it intersects.
It has the +4. Because it has a +4, it's affine. What about the third one? Somebody else? Theo?
Yeah, it's also just bias is 0.
It's affine. Yes? It just happens to be that the bias is 0. And what about the fourth? The fourth is also affine. So you get the idea what we mean by affine. You just have a weighted sum of values plus a bias, and this is passed through an activation function, right? So this is great. You get it all. Now, so we've defined the individual perceptron. But we found in the last class that an individual perceptron is not enough. We really have to begin constructing networks of these perceptrons to be able to compute functions. And so the way we did it was that we had perceptrons which you might have some input, and the input would go into perceptrons. The output of these perceptrons would go into other perceptrons, and so on until you got the final output. So you had a multi-layer perceptron, where perceptrons fed into layers of perceptrons, fed into layers of perceptrons. What is a layer? We'll get into that in a minute. So the networks that we speak of today are deep neural networks. Virginia, what do you understand by the term deep in this context? Multi-layer. How many layers? Okay. So there's a formal definition of depth. What is a layer? Right. So you're taking a lot of these things for granted. You just assume you know, but these are formally defined. And so let's get through the definition. to understand the definition of depth, we have to understand that these networks are just graphs. You have nodes representing individual units that are feeding into under other nodes, which represent other units, and so on. And so I can model them as a graph. There's a source, which is the input, and the sink, which is the output. So it's a directed graph with information flowing from the source to the sink. And in any graph, the depth is very cleanly defined. So the depth of a graph is the length of the longest path from a source to a sink, any source to any sink, right? So in the first graph, there's a path of length 1 from the source to the sink. But the actual depth of the graph is 2 because the longest path is 2. What about the second graph? What's the depth? Anybody? 3. It's written on the screen, so it's easy, right? But then there's a path of length 1, there's a path of length 2, there's also a path of length 3. So the depth of the graph is 3. Now, what is a deep network? A deep graph, by definition, is a graph that has a depth greater than 2. Anything less than 2 is called shallow. So when I have neural networks of this kind.
Question, sir.
Yes. What is the question?
Yes, sir. Please, I wish to know if the depth of the graph depends on whether the graph is directed or undirected.
Thank you. We are speaking only of directed graphs at this point. Once it's undirected, you get into loops. And once you get into loops, then, the depth is really infinite. Yeah.
Thank you.
No, a depth of 3 is a deep neural network.
Okay.
It's not deep. It's not considered deep. This definition, right? So look at this network over here. All the gray nodes are inputs. So those are sources. The nodes on the top are sinks. And the longest path from any source to any sink over here is 3, length 3. So this is a deep neural network. Or the figure to the right, where each block represents a collection of neurons. You can see that there are paths of length 2, 3, 4, and 5 from the beginning to the end. But the longest path is length 5. So this is a network. The depth is 5. This is a deep network. Now, we're speaking of layers. What is a layer? So I have a graph over here. Can somebody tell me which neurons are in the first layer? Anybody? The input is 0, right? I'm calling it 0. Okay. So what are the first neural layer? Which ones? Can you point out?
The top one? Yeah, and then those two and the.
Okay, so why are those the first layer?
Because the depth is 1. We just take 1 hop to each.
Beautiful, right? So all neurons that are the same depth from the input form the same layer. So in this case, the 4 red neurons form the first layer. The 3 green neurons form the second layer. The 2 yellow neurons form the third layer. And the blue neurons form the 4th layer. So it doesn't matter how I draw them. It doesn't matter how I arrange them pictorially. The notion of depth is very clearly defined. Questions? Okay. Yes.
There is a connection between the black one and the one.
It doesn't matter. It's always the longest path, right? So if you consider this one over here, this is what, the 3rd layer? But I believe this might also have a path of length 2. But it's not the 2nd layer. It's the 3rd layer, right, in this figure. Okay? Yes. The volume is low. How do I increase the volume? Maybe there's something here.
Moving it up a little bit.
Oh, it's.
Yeah.
Is this any better, guys, on Zoom? I should hope so. Okay, I can't yell any louder, so this is the best I can do. All right, questions? Yeah.
So let's say layer 1 connects to input as well as layer. So like layer 1 connects back to the input or something like that.
That would be a looping network. So it's eventually it wouldn't be a layer 1, right? It would be the infinite layer because you can keep finding paths. When you're speaking of depth, you're always speaking of directed graphs. If it's directed acyclic graphs with sources and sinks, yes.
Could you please go a slide back? I had a question on the previous slide.
This one?
No, the one before that.
Yeah.
Yeah. The topmost layer, like, how is the LCN size 5?
Which one? This
In red at the top.
I'm not sure what else.
It says LCN.
I just picked up this picture from somewhere. The concept I'm trying to clarify over here is depth, right? That's it, yeah. Ignore everything that I'm not talking about. Now, so here's the multi-layer perceptron. It's a layered network of perceptrons. But then as it happens, any network is layered because things have depth with respect to the input. The inputs can be real or they can be Boolean. The outputs can be real or Boolean. And you can have one or more inputs and you can have one or more outputs. Here's the general structure. What kind of functions? We know that this network is a function. What kind of functions can the network compute? What input-output relationships can it model? And what are the limitations? That's what we're going to cover in the rest of the class. So again, to reiterate, we know that MLPs can compose Boolean functions. We saw this in the last class. We also saw that they can compose real valued functions. They can compute output real valued, generate real valued outputs. What are the limitations and how does it relate to the structure of the network? Again, what do we mean by the structure of the network itself? So that's what we're going to cover today. We're going to talk about multi-layer perceptrons as universal Boolean functions and the need for depth. We're going to talk about MLPs as universal classifiers and the need for depth, and as universal approximators. And once again, we're going to talk about depth and the trade-off between depth and width. So let's look at the MLPs as Boolean functions. First, how well do MLPs model Boolean functions? Now, we don't have to go all the way to an MLP. I can start off with a single perceptron. And we already know that a single perceptron can model various Boolean gates. So what was the gate on the top left from the last class? Anybody? And the bottom. And then there was a knot, right? This was easy. But guess what? This, you'd think, okay, so the threshold gate is just a standard Boolean gate. What have you brought to the table? Well, you brought a whole lot of other stuff. This was one of the reasons that people got confused about the power of these units way back when, because this threshold gate can perform computations that would need an exponential number of Boolean gates to compute if we were doing this using only Boolean gates. So let me give you an idea, right? First, it turns out that a threshold gate is what I call a universal AND. So what is called a universal AND. Here, for example, this gate has, this perceptron has n inputs, but it will only fire if the first L of them are 1 and the remaining are 0. So let's see how that happens, right? If I have L of them, 1 through L, and the rest of them. Now, I'm going to assign a weight of 1 to all of these and a weight of -1 to all of these, right? Now, consider what happens when the first L are all 1 and the remaining are all 0. What is the total input that comes in? Anyone?
L.
L, right? So at this point, this is going to be L. What happens if I flip one of these guys? What happens? It becomes lesser. What happens if I flip one of these guys? It also goes down. So if I just use a threshold of L, this is going to specifically fire when the first L entries are 1 and the remaining are all 0. Now I can flip this. I can construct a unit which does the exact opposite, which means that it will fire if any one of the first L is 1, or if any one of the remaining are 0 is 0. So how can I do that, right? Now, what is the only condition under which this will not fire? What are the conditions under which it will not fire? It must fire if any of these, so these are L, it must fire if any of these is 1 or any of these is 0. So what is the condition under which it will not fire?
All one. Everything at the bottom is one.
If all of these are 1 and all of these are 0. That's the only time it will not fire, right? And I'm still going to use the same kind of weights. These are all 1s and these are all -1s. What is the total sum over here?
Minus L.
That's going to be L minus n plus 1, right? Actually, it's going to be L minus n. So when this, under the condition where nothing, where it doesn't fire, the sum is L minus n. If I flip any one of these guys, what happens to the sum? If any of these becomes a 1, what happens? It increases to L minus n plus 1, right? So also if any of these becomes a 0, that term stops subtracting. It's going to become L minus n plus 1. So if I use a threshold of L minus n plus 1, I get a unit, a single unit that's going to fire if any of the first n is 1 or any of the remaining is 0, right? So beautiful, and it's just one unit. As you can see, it's pretty powerful. It's a pretty universal OR gate, a universal AND gate, but this is still a Boolean gate. Here's something that you can't do with a Boolean gate. I have n inputs. It's going to fire if at least k inputs are 1, right? This is a generalized majority gate. I'm not specifying which k. Any k can be 1, so long as k inputs are 1. If you want to do this with a Boolean gate, no Boolean gate is going to do this. In fact, you're going to, if you want to build a Boolean circuit, you're going to need 2 raised to k gates or 2 raised to n gates to capture every possible pattern under which this can fire or not fire. So something that I'm doing with just one gate is going to take an exponentially sized Boolean circuit, which is why people thought this was so powerful. It's a universal Boolean machine, but it's not, okay? But then we found this cannot do an XOR. We saw this in the last class. To compute an XOR, we need something of this kind, where you have one unit which computes an OR, one X or Y, another unit which computes not X or not Y, and then you AND the two, and now you can get an XOR gate. So although this can do all kinds of crazy magic, if you want to compute the very humble XOR, you need a multi-layer perceptron with 2 hidden perceptrons and 1 output perceptron. In fact, you can get away with just 2. So here is the multi-layer perceptron that gives you an XOR. It has only 2 units, okay? But then once we realize that you can compose Boolean gates and we can compose, things that are more powerful than Boolean gates, you can compose pretty much any Boolean function. So give me a crazy function and I can compose a multi-layer perceptron that will compute it. So this is why we call it a universal Boolean function, in that for any Boolean function, there is an MLP that can compute it. You may not know what the MLP is, but there probably exists an MLP that can compute it, right? But then, if you look at this picture over here, how many layers does the MLP on the left have? Anybody? How many layers does it have? So what is the total? 3 layers, right? Or I can have some, or I might need something more complex like the one to the right. So how does the complexity of the Boolean function relate to the depth of the network? Anybody want to guess? Yes.
So the K is the depth.
Do you think it's exponentially sized? What if I told you that regardless of the Boolean function, I can compute it using only one hidden layer? Would you believe me?
There's no restrictions on width.
So what is a Boolean function? A Boolean function is just a truth table. I have a certain number of inputs, and I can list out the output for every pattern of inputs. In fact, I don't need to do this for every pattern of inputs. I only need to list out the outputs for the input patterns for which the output is 1, right? So here is a Boolean function. It has 1, 2, 3, 4, 5, 6 possible combinations under which the output is 1. And so I can write the Boolean function very simply. I can say, let's look at the first guy. the output must be a 1 when the inputs are, this is x1 through x2, x3, x4, x5. So the output must be a 1 under the condition 0, 0, 1, 0, 1, right? Which is like saying this is x1 bar, which means when x1 is 0, this becomes a 1, right? x2 bar, x3, x4 bar, x5. So this is x1 bar, not x1 and not x2 and x3 and not x4 and x5. That's what this clause is. Under this combination, the output is 1, right? I can write one such clause for every combination for which you have an output of 1. So this is the famous disjunctive normal form, where I have one clause for every combination for which the output is 1, and I OR the lot. So the ANDing is represented as a multiplication, the OR is represented as a summation, and so this is a sum of 6 clauses, each of which is a product of 5 terms. And this provably computes this function. It doesn't matter how complex the function is, I can always write it in this form. How many layers will if I want to do this with a neural network, how many hidden layers will it need? It's going to need one perceptron for the first clause, second for the second, third for the third, fourth for the fourth, and then I OR the lot. So a multi-layer perceptron with just one hidden layer can compute any Boolean function. So this is great, right? They are not only universal Boolean functions, you can do it with just one hidden layer. So what's the catch? The catch is the number of clauses you have. So you're going to need as many neurons in that hidden layer as the number of clauses in the DNF formula. And to understand the limitation on this, I'm going to look at a different way of representing a truth table. How many of you are familiar with Carnot maps? 1, 2. A small number. Most of you do not know what a Carnot map is. If you're an electrical engineer, you'll probably encounter it. If you've done computer architecture, you'll probably encounter it. So I get some idea of the kinds of courses you guys have taken. But the Carnot map is a topological representation of the input. So you look at the 4 rows over here. This is a function of 4 variables, wx and yz. These 4 rows represent 4 combinations of w and x. So this is where wx is 0, 0, 0, 1, 1, 1, 1, 0. And what you observe is that adjacent rows differ in only 1 bit. So also the 4 columns represent the 4 combinations of y and z, and adjacent rows only differ in 1 bit. And each cell over here, therefore, represents one combination of the 4 variables. So this one over here, for example, is wx is 0, 1, yz is 1, 1. So it's 0, 1, 1, 1. And now I can represent the truth table by highlighting the cells for which the output is 1. So there are 7 cells over here for which the output is 1. So if I were to write a naive DNF formula, how many clauses would it have? 7, right? But then I can simplify it. If you look at this figure, you look at the first column, the output is 1 for all entries in that column. What does it tell me? It tells me that the values of wx do not matter. The function fires regardless of what w and x are. So by grouping these guys together, I'm left with the information that I only need to make sure that y, z are 0, 0, then it will fire. That gives me the clause not y, not z, right? So also I can group these two together. And by grouping these two together, I'm discovering that the value of z doesn't matter. Because it's going to fire for both 0, 0, and 0, 1, so long as w and x are 0, 1, right? So this gives me the clause not w, x, not y, z can be ignored. So by grouping adjacent elements together into the largest possible groups, I can reduce the number of clauses in my DNF formula. This guy can be done with just 3 clauses. And so my hidden layer is going to only have 3 neurons. Now, if I'm looking for the worst case, I'm looking for the case where the number of neurons in that hidden layer is the largest. What is the condition under which I will have the largest number of clauses in the hidden layer? That is, what is the condition under which I simply won't be able to group things? Yes? Beautiful, right? If I have a checkerboard pattern, You take any two patterns, the minimal difference between the two is 2 bits. There's no way I can group it. And so over here, how many clauses would my DNF formula have? 8. If I were to build an MLP with just one hidden layer, it's going to need 8 neurons. If I had the 3, right? So if I had a 3-dimensional version of it, this has 64 possible combinations of 6 variables, but I can have the same alternating pattern. How many neurons would the hidden layer have over here if I had just one hidden layer? 32, right? So can one generalize over here for the worst case? Thank you, right? You're going to require 2 raised to n minus 1 neurons in the one hidden layer if you're just restricting yourself to one hidden layer. The number of neurons is going to be, perceptrons is going to be exponential in n. Right? I'm doing this naively, I'm lying a little bit, but I'll let you figure this out, okay? The basic concept still holds. So this means that in the worst case, the size, if I'm trying to implement my function using just one hidden layer, I'm going to require an exponential number of neurons in the first layer. But does anybody recognize this function? Anytime 2 bits change, the output changes. What kind of function is that? Anyone? What function changes every time you change a single bit? It's an XOR, right? This is an XOR. So, but first, before that, there's a poll. It is. Yeah. So linear functions are affine, affine functions are not linear. Okay, we're out of time. Anybody want to answer this?
512.
512, right? Beautiful, thank you. So let's go back here, right? The reason these networks got to be exponentially big, they got exponentially wide. That one hidden layer needed 2 raised to n minus 1 neurons, correct? So that is the width, how many neurons you have in the layer. Now, that was because I had only one hidden layer. What would happen if I permitted depth? So let's go back and look at the function again. We know that these are XORs. Now, if I'm doing an XOR, how many neurons did we require to compute a single XOR? 3, if you do it naively, 2, if you do it, a little smartly, right? So over here, I can rewrite this. The first one is going to be X XOR with Y. I can compute this, and this is going to need how many neurons? 3 or 2. I'm going to assume 3 for now, right? This output can be X, Y, this is W and X, right? W and X. And this can be XORed with Y, right? So this is going to need 3 more neurons, right? And that output can be XORed with Z. And so if I were to draw this, that's going to, we know that an XOR takes 3 perceptrons or even 2. So this guy can simply written as XOR, a single XOR for W and X, a single XOR for the output of that in Y, and a single XOR for the output of that in Z. How many neurons would this take? Anybody? It's going to take 9. It's going to take, okay. If I were to use the same structure for the problem to the right, how many neurons will it take? 15? Why? 5 XORs, right? Does anybody see a pattern? What is the pattern?
Number of variables minus 1.
So the XOR of n variables is going to take 3 times n minus 1 neurons, right? And I got this by permitting depth, right? And so Once I take this network, which is shallow and wide, if I permit depth, the number of neurons I require can fall exponentially. So a network that required an exponentially sized number of units when it was done using just one hidden layer required a linear number of units when depth was permitted. That's why depth is important. Now, what is the limitation on this depth? We also have a number for that, and we're going to continue considering this worst case for XORs. And so here's how we're going to do it. Now, an XOR is associative, right? If I wanted to compute an XOR of, W XOR Y XOR, W X XOR Y XOR Z, I can do it this way. I can first compute the XOR of W and X. I can compute the XOR of Y and Z, right? So these guys. And then these, I can compute the XOR of this one, and that's going to give me the XOR of all four. So in general, if I have a very large number of variables, I can begin by pairing them up and computing the XOR of pairs. Then I can compute the XOR of pairs of those outputs and then pairs of those outputs and so on. If I did it in this manner, how many layers would I need?
Log of n.
Log of n, right? 2 log of n, because you need 2 layers for each XOR. But then what this tells me is that I can get away with a linear number of units if the depth that's permitted to me is 2 times log of n. What would happen if I said that you're not allowed 2 times log of n layers? You're only allowed 7 layers. What happens? How? Anybody? Yeah.
You go to 6 like this, and then use the single.
Right. Fantastic. Right. You can shrink it by 2 raised to by a factor of 32. But then after that, you're left with only one hidden layer. So from there on, it's going to be exponentially sized. So what this means is that if you limit the depth of the network, suddenly you find yourself in a situation where the number of units you require is exponential in the size of the input. So there's a very nice theorem. There are several theorems to this effect that that in the worst case, for any Boolean function, if you limit the depth of the network is going to be exponentially large. The only time where you can get away with a linear number of units is if the depth of the network itself is a function of the number of inputs. Over here, we found that to be log base 2 of n, right? So deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using only one hidden layer. And so in summary, an MLP is a universal Boolean function, but can represent a given function only if it is sufficiently wide. Because if I decide to restrict myself to just one hidden layer, I need 2 raised to n minus 1 units. What happens in the XOR case if I have 1 unit less? What will the error be? Can anybody tell me? In the XOR case, if I miss just 1 unit, what will the error be? Anyone? Give me a number. What fraction of the time will I be wrong? Just 1 unit. Half. In the case of the XOR, it's the worst case. If you miss 1 bit, the error becomes 50%.
Which means
it's pretty much random, right? So if you don't have 2 raised to n minus 1 units in that one hidden layer, and you skip just one guy, then you might as well not compute the function at all. That's going to be random. Okay. So it can represent the function only if it's sufficiently wide, and if it's sufficiently deep, But there's a trade-off. If you make it deep, you can reduce the width, and but it's not universal. There are cases where you can't quite do this. And the optimal width and depth depend on the number of variables and the complexity of the Boolean functions, where I can quantify the complexity of the Boolean function in terms of the number of clauses in the DNF formula. So the story so far, MLPs are universal Boolean functions. Even a network with a single hidden layer is a universal Boolean machine. But a single layer network may require an exponentially large number of perceptrons, and deeper networks may require far fewer neurons than shallower networks to express the same function. They could be exponentially smaller. Any questions? Questions? Yeah.
Are neurons analogous to storage space while depth is analogous to runtime?
The number of neurons is analogous to runtime, right, effectively. You're going to have to process every one of them. So what depth does do is to sequentialize the process. And so depth has the aspect of sequentiality of computation, which also affects runtime.
Hi, Professor from Zoom.
Yes. Yeah.
In general, in practice, when given the choice, do you prefer limiting the number of neurons? I mean, the nodes, or limiting the number of layers, or it depends on the situation?
So we will get to that, right? Because we're speaking of Boolean functions, you want to reduce the number of computations in the end. So you want to have the architecture that permits you to get away with the smallest number of neurons overall, which might mean that you want to have narrow but deep networks. But we'll see more of that. So we've seen how networks can be, neural networks are universal Boolean functions. We're going to see how they operate as universal classifiers. Now, once again, we saw this in the last class. If I begin operating on real valued inputs, the multi-layer perceptron operates on a bunch of numbers, and it can demarcate a region of the space and say everything inside gets an output of 1, everything outside gets an output of 0, right? So it finds it's a function that finds a complex decision boundary over the space of reals. And we saw how we did this. Once again, going back to the simple threshold activation, if I have the activation that says summation wi xi greater than or equal to 2 implies 1, then there's a boundary between where the output is 1 and where the output is 0. And the boundary is where summation wi xi is exactly equal to t. That's the equation for a hyperplane. So in the space, there's a hyperplane where inputs on one side of the hyperplane will always generate an output 1, and those on the other side are always going to generate the output 0, right? So if I were to plot the function, it's going to look like this Heaviside function over here. There's a hyperplane. As you walk along the space, right until you get to the hyperplane, the output is 0, then you step up and you begin outputting 1. It's a linear classifier, meaning the boundary between where the output is 0 and where the output is 1 is linear. Now, it's a hyperplane, okay? And we saw how this is what controls the fact that this can be used to perform Boolean operations. If the inputs are Boolean, they're all zeros and ones, then having the decision boundary be here between is going to result in a what was that? There was an OR, right? Having it here generates, what is this one? Anyone? What's the second picture? Yeah.
Not y.
It's ignoring x, it's just not y, right? And the third one, is this possible using a single perceptron?
No.
Why not?
Two boundaries.
It's got two boundaries. That's why you cannot do an XOR with a single perceptron. You need two boundaries, right? And so here's a pull. Okay, time's up, guys. Anybody want to answer this on Zoom? True or false? Zoom.
True.
True, thank you. Right? Easy. An XOR needs two hidden neurons and one output neuron because we need one hidden neuron for each of the two boundaries and an output to AND them. That's basically how we did it. And the reason we managed to get away with two neurons rather than three is to basically combine operations. The first neuron told you if you were to the left of the first line, and the second one told you if you were to the left, to the right of the first line and to the right of the second line. Okay. Now, but then we saw how we can use this simple structure to compose more complex boundaries by combining them. If we wanted the pentagon, pentagonal decision boundary where the output is 1 inside the pentagon and 0 outside, I'd have 1 perceptron for the lower boundary. So this is going to output a 1 above the line and 0 below it. I have 1 for the guy to the right. It outputs a 0 to the right and 1 to the left, and so on. So I have 5 such boundaries, 1 for each side of the pentagon. And then, okay, tell me this. Here is this is interesting and this is important. If I look at the sum of the outputs of all 5 neurons, and I have this pentagon, this is the decision boundary that I want. Oh. I hope everybody can hear me. Okay. So what is the sum of the outputs of the all 5 neurons inside the pentagon? 5, right? What is the sum outside? Is there any region outside where the sum is 5? No. So that's why we can actually just compute a threshold of 5, compare the sum to a threshold of 5, and you get the pentagon decision boundary. But then look at the sums in the other regions. The sum over here is 4. If I were to use a threshold of 4, what would the decision boundary look like? It's going to look like a star. If I were to use a threshold of 3, what's it going to look like? It's going to be a large decision boundary where it's ignoring some spaces, right? It's going to ignore everything that's a 2. So you can construct fairly complex decision boundaries. There's no restriction that the decision boundary that you compute is convex. But then, if I want to compose this double pentagon, the way I would do it was to construct one subnet for the first pentagon, another for the second pentagon, then I would OR the 2, and therefore I'd get the double pentagon. Easy. And then once I know how to do this, I know how to compute other kinds of decision boundaries, like these crazy figures that you have, including the one in the shape of a horse. All I need to do is to decompose these decision boundaries into little regions, for which I do know how to compose the boundary, and then I can OR the lot. And this requires at least 2 layers. If you want to simplify it, at least 2 hidden layers. If you want to simplify it, if you want to simplify the structures, you're going to need more hidden layers. So my question is, can I compose this with only 1 hidden layer? Let's go to a simpler problem. How would you compose this decision boundary, the double pentagon, with just 1 hidden layer? I'm going to give everybody like a minute to think about it, and I'll ask for suggestions. Just 1 hidden layer. You guys here, any ideas?
Can I try from Zoom?
Yes, sure.
Do the regions, like for example, the first pentagon, do they all points in that pentagon have a same sum or something? And then you can have like sum 1, either x1 or x2 as the sum, and then if the sum is either x1 or x2, you can have an AND to create the final output.
So if you make this more complex, how many layers will that have? You're adding layers, right? So here is the problem. And the problem has to do with the sum. The sum for this guy is 4 over here, and 4 over here, and 4 over here, and 4 over here, and 4 over here. Right. The sum for the second guy is going to be 4 over here. So if I combine the two, the total sum is actually going to be 8 over here, 4 coming from the pentagon on the top and 4 from the pentagon at the bottom. So if I use any kind of threshold which is appropriate for the double pentagon, it's going to accept a whole bunch of other regions which are not desired. And this is a problem that we will always encounter in real life when you're building your neural networks. This is the problem that actually causes your neural network to accept things that you don't want it to accept. Because there are regions which you are not planning for, which just come across which just get accepted as an interaction between the layers between the regions that you are trying to accept. So how would I solve this problem? My claim is that you can do this, or you can do this arbitrarily correctly using a single hidden layer.
Professor,
Yeah.
could you do it by negating the parts that are outside both pentagons?
So the point is, if gating is another layer.
No, negate it like in the same layer. So you do a universal AND with negates of the white regions.
Yeah, but then if I'm going to negate those regions, that's an extra logical layer, is it not?
Wouldn't you put it on the same layer as all the other regions for the pentagon?
Okay, so I suggest that you actually think about this and try to draw the example, and you will see that in every case you're going to need more than one layer. There's in fact only one way to do this, and that's like this, right? So let's go back and look at the same example, but now I'm going to start with a diamond. And for a diamond, I need 4 boundaries. And if I look at the sum of the outputs of the 4 neurons, the sum is going to be 4 inside the diamond. Then there are all those regions, the yellow regions, which go out to infinity where the sum is 3, and the white regions where the sum is 2. The lowest sum is going to be 2, okay? If I have a pentagon, so this figure to the top right, that's basically just showing the sum. If I slice it at 4, it's going to give you the diamond decision boundary. Now, if I have a pentagon, that figure to the top right is showing the sum. It's not very cleanly drawn, but you get the idea, right? And so the sum is 5 inside. It's 4 inside those little triangular regions, 3 in the big spaces outside, and 2 in the slits to the corner. But look at what happened to the region that was sum 3, which is just 1 below the count of 4. That had infinite area over here. Now it's finite area, right? So if I go up to a hexagon, that figure to the top right is the sum again. And you can see that region where the sum is 5 and not 6. And that has shrunk in area again, correct? And so what do you think will happen as I keep increasing the number of sides? Anybody? You're going to get something that approaches a cylinder, right? This is a heptagon. And inside the heptagon, the sum is 7. The region where the sum is 6 is much smaller. The region where the sum is 5 is larger, 4 is larger. It never goes below 3. This is with 16 sides. The lowest sum you're going to get is 8, and it's 16 inside the heptagon, inside the 16agon, whatever it's called, right? This is with 64 sides. This is with 1,000 sides. As I keep increasing the number of sides, what will the figure eventually become? It's going to look almost cylindrical. There's a mathematical formula that you can derive. This was, in fact, the formula was given to me by one of my ideal undergrads. And I presented it in class. He came back after class and he had worked out the formula, so I plotted it. Anyway, so it's n inside the circle, n minus 2 outside. And I can make the width of the circle arbitrary. If I make the circle small enough, this is going to end up looking like an almost perfect cylinder, where the sum is n inside and n over 2 outside. So if I were to add an extra bias element, which subtracts out the n over 2, then the sum is going to be n over 2 inside the cylinder and 0 outside. So now here's the beautiful thing. If I have something of this kind, then I can have one subnet. This only works for very large n, right? Because you're increasing the n and it's getting closer and closer to a circle. So at this point, this guy can have a very large number of units, and the sum is going to be something like this. It's a cylinder at some location. I can position the cylinder anywhere. I can make it, and I can also adjust the width, right? Now I can have a second subnet of this kind with many units. And then this could be a cylinder in a different location, right? So what happens if I sum these two guys up? If I sum these two guys up, wherever this is an n over 2, this is a 0. wherever this is an n over 2, this is a 0. So the sum of the two is simply going to look like two cylinders, right? And I don't need two sums. I can just make the whole thing one big sum. This makes sense? Right, and so now I can actually have two subnets, each composing its own cylinder at its own location. And now if I use a threshold of n over 2, I'm going to get a decision boundary that's two disconnected circles. Magic, right? You wouldn't have thought it. And then if I want to compose this guy, this is how I would do it. I'm going to fill it up with circles. And I can make this, is this exact? What is it?
Approximation.
How accurate is the approximation? I can make it arbitrarily accurate by making the circles smaller and packing them together, right? You give me an error bound, I can compose an approximation that has an error below it, but the error is never going to be 0.
Recording in progress.
Right? And so MLPs can capture any classification boundary. A one hidden layer MLP can model any boundary, which means that MLPs are universal classifiers, meaning you give me a boundary, you give me an error, I can compose an MLP that gives you that boundary with error below whatever you want. And moreover, I can do this with just one hidden layer. The problem, of course, is that you don't want to do it with one hidden layer, right? But in this case, it's very obvious that the difference between having it with one hidden layer versus just having two hidden layers is the difference between requiring infinite neurons in that layer versus requiring only 12 hidden neurons. That's why depth is important. And that's why it trades off for an exponential increase in the width. Questions?
Are you saying that it's not a fully connected layer here, or just like
Which one?
the
Figure to the left? So in this case, I know that, so this is a figure, this is a network that definitely gives me this boundary. You could connect it fully and try to learn it, but we haven't gotten to learning yet, right? But that is a network that definitely computes that boundary. So I'm giving you an example of something that does give you the answer. Right? Yes.
So earlier we said that any network with less than greater than 2 layers is a deep neural network.
Yes.
So, but this is like having infinite perceptrons is equivalent to having a multi-layer neural network. So
that's infinite perceptrons in the one hidden layer. So it's still depth 2. It's not deep. Right. The moment I make it deep, the moment I add more layers, I can reduce the width.
But it wouldn't be a 2-layer, no? So like
if I have infinite neurons in the hidden layer, what is the depth? It's still 2. The longest path is from the input to the hidden layer to the output, correct? Depth is how many steps you take. Okay. So I'm going to look at a slightly different pattern, a worst case decision boundary of sorts. Again, the example I'm giving you is slightly fraudulent, but it will give you it conveys a concept. And I'm going to assume threshold activation networks, and we'll show you how you can generalize beyond threshold activation networks in a few minutes. So let's say I have this decision boundary where I want this checkerboard pattern. I want an output of 1 inside the yellow regions and a 0 outside. Then if I want to do this naively, I'm going to need, with just one hidden layer, I'm going to need infinite neurons in the hidden layer. We've already seen this. But I can do this with 2 hidden layers in this manner. The boundary, the checkerboard is composed of 16 lines. So I can have 16 neurons in the first hidden layer, where each of them tells me whether I'm to the left of one line or the right, or above or below, right? And then so I have captured each of the 16 boundaries, these guys. And then after that, I need 40 neurons for each of the yellow regions, because each yellow region combines up to 4 of these boundaries. And then finally, I need an OR. So this decision boundary can be captured using just 57 total neurons. But then does anybody recognize this pattern? Again, what is a checkerboard?
XOR.
It's an XOR, right? So this is just an XOR of the 16 lines, which means that I could have done this with 61 neurons if I use 3 neurons per XOR, or 46 neurons if I do this with 2 neurons per XOR, meaning I get a reduction. Now, this is a very simple pattern. If I had something more complex like this with a grid formed of 64 lines, then I'd need 64 basic units, first level units, to capture the bound lines. And then I'm going to, okay, do you mind shutting the laptop? Huh? Oh, yes. I see the laptop and not you. Okay. So, so the 64 lines for the first layer, and there are 544 units in the second layer. So I'm going to need 544 of those guys, right? But then if I do this with XORs, I can do this with 190 neurons. So even in real life problems, you're going to encounter these situations, right? Yeah. So the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input. Or alternately, if you want to think of this in terms of features in the input, it can be, in the worst case, exponential in the number of statistically independent features that you can derive from the input. Yes?
In the checkerboard pattern, how were the number of neurons in the second layer?
The number of yellow regions.
The number of?
Yellow regions, the boxes. Right, you need one for each of these. Okay, so the story so far, adding to the universal Boolean machine and the universal classification function. We said that even a network with a single hidden layer is a universal classifier, and a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower ones to express the same function. And they could be exponentially smaller. So deeper networks are more expressive, right? So we've looked at classifiers. Now let's look at approximators. Same thing. We saw in the last class how I can compose one hidden layer, how I can compose a multi-layer perceptron to capture any scalar function of a scalar variable. So I could start off by this little network, which is going to produce an output of 1 between the thresholds T1 and T2 and 0 elsewhere. So now, given a more complex function, I can partition the domain into many small regions and then have the network have one pair of neurons, output of 1 within each region, scale each of these outputs up to the average height of the function within that region and sum them up. And so you're going to get a stepwise approximation to the function, and I can make this approximation arbitrarily precise, meaning you give me an error and I can come up with an approximation that's lower than it. But this is for a scalar function of a scalar variable, right? How would I do this with higher dimensions? Turns out there's no simple way of doing this with higher dimensions. If I want to do this in higher dimensions, I must go back to my cylinder, where I need a large number of neurons just for the basic cylinder itself. And then, if I want to compose a function, I'm going to basically fill up the space with cylinders, where the different cylinders are scaled to the right height. And once I do this, then give me the function, and I can compose a single hidden layer network, which approximates the function to arbitrary precision, right? And so here's a poll. Yeah. Okay. Okay, 15 minutes, 15 seconds, guys. I don't have 15 minutes. All right, this is an easy one. What is the answer? Anybody? False. Why is it false?
It will be approximated.
It can only be approximated, correct? Thank you. So you guys have got it. At least those of you who answered have got it. Now, so now let's look at this last topic, the notion of sufficient width and sufficient depth, and how activation functions interact with this notion of sufficiency of width and depth. So in the previous discussion, we've shown that a single hidden layer MLP is a universal function approximator. It can approximate any function to arbitrary precision, but it may require infinite neurons in that one hidden layer. More generally, we saw that deeper networks will require far fewer neurons for the same approximation error. This was true for Boolean functions, it was true for classifiers, and it was true for real-valued functions. But there are limitations. So this seems to give us the impression that I can reduce the width and exchange it with depth, and I should be able to model the function. Can I just keep doing this arbitrarily? And the answer would obviously be no, right? In the worst, because in this, that seems to tell me that in the limiting case, I can reduce the width to 1 and make the depth infinite, and I should be able to capture any function, and you cannot. And we will see why, right? So let's go back to this simple net function again. This has 16, this is the checkerboard composed of 16 lines. So I can do this using 16 neurons in the first hidden layer and 40 neurons in the second hidden layer because there are 40 yellow regions. So we're going to use this to, we've already seen that a neural network can represent any function provided it has sufficient capacity. By capacity, we mean it has sufficient depth and sufficient width. But we're going to see that not every architecture can represent every function. There is a limitation. And for this, let's look at this example again. Suppose instead of having 16 neurons in the first layer, I only had 8. And I'm going to assume that we have threshold activation functions. So we'll stick with threshold activations. If I have only 8 neurons in the first layer, can I make up for this by adding more layers and more neurons in the subsequent layers? Why not?
See this information.
You have lost information, right? So similarly, because what those 8 neurons are going to tell you is whether the input is on the left or the right of some arbitrary set of 8 lines. So it might tell you just this. It's going to tell you in which of these strips the input lies, but there is no additional information. It doesn't tell you where in the strip the input lies, which means that the subsequent layers can never hope to catch up. The information is quite gone. Even if those first 8 neurons were to capture these boundaries, which look somewhat like the checkerboard, I'm still only going to have some information about the specific cells of this grid within which the input lies, but no information about where in the grid the input lies. And so I can no longer hope to reconstruct the rest of the decision boundary. That makes sense to everybody? Right? So, same thing. Even if I have 16 neurons in the first layer, so I've managed to capture all 16 lines. If I have fewer than 40 neurons in the second layer, there's no way I can actually hope to capture all 40 cells. So which tells me that in each layer, there's a minimum number of neurons that are required for me to be able to capture the decision boundary, capture the function that I'm trying to capture. But there was one little caveat in all of this. And the caveat is that I assumed a threshold activation function. Now, and the threshold activation function has this nasty property, it gates information. It only tells you whether you're on one side of the threshold or the other, which means that if I had only 4 neurons in the first layer, I would only get information of this kind, telling me which strip the input lies in. And that is not enough information for subsequent layers to actually recover the decision boundary. So if you as smart young computer scientists were given this problem, how would you change? What would you change to make this better? Anybody? Thank you. This is beautiful, right? So thank you, Shrey. That's exactly what you want. You want the activation function to not just say whether you're on one side of the boundary or the other. You want the activation function to continue to give information, how far you are from the boundary. So if you were using a sigmoid, for instance, then the sigmoid is not merely going to tell you whether you're to the right of the boundary or to the left, but as you go away from the boundary, the value changes. So now you have additional information for the downstream neurons that could potentially work on this and decipher more information to construct the boundary. Here you see something interesting. The sigmoid flattens out very quickly, which means that the sigmoid gives you information about how far you are from the boundary for a little time or a little distance, and then it's done. So can you improve on this? What kind of activation would you use to improve on this? Tan H is also going to saturate on either side, correct?
Linear approximation.
Linear approximations. Any ideas? Yeah, I'm hearing some good ideas. Anything else? Guys on Zoom? Yeah, lovely, right? So here, a ReLU is going to continue to give you this information forever, but only on one side, right? On the other side, you have lost the information. So maybe you need a different variant of this kind, which gives you information about how far you are from the boundary on both sides. Now, once you begin presenting this information to downstream neurons, you can get away with just 4 neurons in the first layer, or not quite fully, but at least recover part of the information. So there's always a minimum, a sufficient width, below which it doesn't matter how you adjust those guys, you've lost information. But within those restrictions, by having better activation functions in the neurons, which actually give you information about how far you are from the boundary, you are conveying sufficient information, or hopefully conveying sufficient information to downstream layers that they can actually reconstruct construct the decision boundary. So you're able to trade off to some extent depth width for depth. When you make it narrower, you're going to have to do more work down the network. But again, we also saw that deeper networks are more powerful, so you get the trade-off is not a bad thing. So narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded, but they require greater depth to permit later layers to capture patterns. And so the lesson so far, MLPs are universal function approximators. They can model any Boolean function, classification function, or regression, meaning if it's computing a continuous valued output, right? And deeper MLPs can achieve the same precision with far fewer neurons, but must still have sufficient capacity, meaning the activations must pass information through, and each layer must still be sufficiently wide to convey all relevant information to subsequent layers. Questions? Yeah.
How does the ReLU activation function convey more information to subsequent layers than like a simple linear layer?
Does the linear layer have a boundary?
No, like the linear layer would give you information on both sides of the boundary.
Does it have a boundary? Does it have any change in behavior?
No.
So there's no notion of depth. I can compose an arbitrary number of linear transformations into a single linear transform. Right? That's just a linear transform. The magic of this is by having these little nonlinear units, you can compose arbitrarily complex nonlinear functions. With only linear units, you can never do that. Right? So there's a final poll. I will give you the full minute and a half because there are 4. I was using Miguel as my clock. Okay, guys. Does anybody on Zoom want to tell me if the first statement is true? Zoom?
It's not true because we just showed the 16 versus 8 like strip example.
Thank you. Lovely, right? So somebody here, Vinayak, what about the second statement? Is that true? Okay, Yash?
I think it is true.
It is true. All right. She1, is the third statement true? It's not. Somebody at the back, Chris, do you want to answer if the fourth statement is true? Let's check if they're right. Only the second and fourth statements are true, right? The first statement is false, as we just showed. Networks with graded activation functions are more able to compensate for insufficient width through depth than those with threshold or saturating activations. We just saw that in the lecture. You cannot always compensate for limits in the width and depth of the network by using graded activations, as I just explained. There's a point beyond which you just lost information. There's nothing you can recover. If you project it into a lower dimensional space, you're done, right? For a given accuracy of modeling a function, networks with more graded activations will generally be smaller than those with less graded activations because you're conveying more information to the deeper layers. And so we get to the end of this lecture. There's a notion of a sufficiency of architecture. I tried to explain this with pictures and simple, visual illustrations, but of course there's a whole ton of math behind it. For those of you who are mathematically inclined, there are papers, but it's my experience that the majority of us would rather not deal with the math. That includes me. And so, but there's a definition. They have the capacity of the network is defined in different ways in terms of information or storage capacity, in terms of VC dimension. From our perspective, it's the largest number of disconnected convex regions it can represent. And we find that a network with insufficient capacity cannot exactly model a function that requires then a greater number of, minimal number of convex halves than the capacity of the network. Well, it sounds complicated, but yeah, you get the idea, right? And there are lots of different papers on the capacity of a network. So the lessons for today.
Sorry, what is VC dimension?
We don't need to deal with it. It's a complicated subject, right? But we can, if you take this on Piazza, I will explain, right? So MLPs are Boolean functions. They are universal classifiers. They're universal function approximators. A single layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely wide in its input. Deeper MLPs can achieve the same precision with far fewer neurons, so they are more expressive, and more graded activation functions result in more expressive networks. That's the end of this lecture. In the next few classes, we know that MLPs can emulate any function, but how do you make them emulate a specific function? That's what we're going to deal with in the next couple of weeks. If you have any questions, I'll take them. Otherwise,
have trouble getting